related to enhancing infrastructure resilience in Taiwan among the challenges of global climate change. Different from the presentation from the previous two speakers, they give the global viewpoint or concept to the smart technology in application to the civil engineering. However, now my presentation just gives some real cases in Taiwan. Okay. And this is the content that we make today. The first one related to the natural environmental in Taiwan. It is very important. We have to understand the environment where we are. Then we can do some strategy to prevent the natural disaster. And we also, I want also make the introduction about the urgent reconstruction of the damaged bridges caused by CICHE earthquake in 1999. And also the scarring of the bridge foundation is very important issue. So how to make the better practical work to prevent it is very, very important. And because we have the natural disaster, so in the future or currently, how can we do? So we just did some basic research and for the bridge design and for the emergency disaster relief. And also we want to announce ABC, accelerated bridge construction. And finally, we just give a real case for the bridge health monitoring and real-time safety assessment. Okay, as you know that the total area is approximately 36,000 kilometers square in Taiwan, and population is about 23 million. As you know that the annual average rainfall is about 2,500 millimeter, and it is very important that with 70% concentrated between May and October. And as you can see now, the 3/4 of the land is in the mountainous, and the population density is very, very high. So you can see now, at least we have 4 natural disasters, including earthquake, typhoon, debris flow, and flood. So how to prevent it is very important. This slide just shows the location of the Taiwan. Taiwan is located on the convergent boundary zone between the Eurasian plate and the Philippine Sea plate. So many faults are distributed on the land of Taiwan. And this slide just shows the river situation. Let's take the cross-section area at the middle side. You can see the in the central zone, the elevation over 3,000 meters. For example, this is the Gem Mountain, and this is the western coast area. As you can see, the distance from the center of the mountain to the sea, the distance is very short. However, the elevation difference is very large. So you can see the slope of the river in Taiwan is far larger than those in the other country all over the world. And according to the World Bank report, Natural Disaster Hotspots, a global risk analysis made in 2005, it is reported that there are 73.1% of Taiwan's land and population are simultaneously exposed to 4 types of disaster. Okay, actually we don't want we stand on the top 1 class in the world for this issue. Okay, this slide shows the weather change of Taiwan, rising of the temperature. This slide for the global average temperature, as you can see, just before the starting from about 1960, the increase of temperature becomes significant. In the most recent 30 years, the rate of increase has accelerated to 0.21 Celsius degree per decade, indicating a more pronounced warming trend. However, just take a look at the situation in Taiwan. As you can see, the increase of 0.11 Celsius degree per decade, and the warming trend in urban areas is more pronounced, with an increase of 0.08 degree per decade compared to the global average. And finally, we can see that in the recent 30 years, the warming trend is even more significant, with an increase of 0.29 degree per decade. surpassing the global temperature increase rate. So this is the average changes situation in Taiwan. This slide just talking about the rising of the sea level. As you can see, just starting from 2000, the trend of the sea level increase becomes significant. And the average annual sea level rise around Taiwan is 2.4 millimeter, which is 1.4 times the global average annual rise of 1.8 millimeter. Okay, I think those three photos will give you an impact. This is a bridge, a bridge in near the outside of the Guguan power plant, Taipei. As you can see, before 1999, the seabed, the distance from the bridge deck to the seabed is very high, at least over 10 meters. However, after 1999, CICHE earthquake happened. You can see lots of debris flow brings the debris, brings the stone to the riverbed here. So the clearance beneath the bridge deck becomes very, very low. And after 2001, Typhoon Toraji occupied Taiwan. And you can see lots of stone occupy totally the bridge deck. So you can see the natural environment change so huge. So how can we do in the future to deal with this topic? It's very important. This slide shows the number of high potential debris flow rivers in Taiwan. As you can see, there are 485 rivers with a high potential debris flow in 1996. However, you can see the number increase year by year. Up to 2023, the number is increased to 1731. So as we know that when earthquakes or typhoons leave a significant amount of debris in the mountains, the likelihood of debris flow occurring increases when accumulative rainfall exceeds 150 meters or hourly rainfall exceeds 40 millimeters. And after an earthquake occurs, the critical rainfall threshold for debris flows will decrease. According to the experience of the Guangdong area in Japan, it should need 50 years to recover the original situation back to the earthquake, before to the earthquake. This slide shows the erosion of the Zhiben River embankment caused by the Typhoon Morak. As you can see, the location of the building originally is far from the riverside. However, when the typhoon, the flood scratched to the river bank, so you can see eventually the building was collapsed. And this slide shows the riverbed change situation for the Shuangyuan Daqiao in Kaohsiung County. Okay, this figure shows the riverbed elevation at a different edge. As you can see, originally the blue dashed line means the riverbed in 1972. As you can see, there is no any deep channel, right? Because you can see the riverbed seems so smooth. However, up to 1981, okay, you can see the scarring depth was observed, and which can be indicated by the green dashed line. And also here we can see there's somewhat large change, but up to 2003, you can see the riverbed change indicated by the yellow dashed line. So here we can see it seems that the channel, deep channel, is happened. And finally, in 2009, the riverbed changes the red line. So you can see the location at the pier 14 here. The scar depth is very, very large. And eventually, when the typhoon, the flood struck the bridge, then the bridge pier, bridge foundation was destroyed. And I will give some examples, just one example for the consideration of urgent reconstruction of the damaged bridge caused by the CICHE earthquake. Because at that time, I was the bridge engineer. And when the CICHE earthquake happens, we spent 1 month long at a disaster zone to have the highway bureau to do the reconstruction work. So the example is related to Wuxi Bridge. As you can see, this is the original planning of the preferred route of the Wuxi Bridge. And the dashed line means the fault. So you can see the fault just cross the pier between the pier 1 and pier 3. Okay. And this is the image of the damage situation in the Wuxi Bridge. As you can see at the pier 1, the pier, the substructure was destroyed, and pier 2 was also. And you can see in 1973, this kind of bridge pier is recognized as world type. Okay, but it is still survived. However, in the 1982, also its construction time is younger than this one. However, it somehow belonged to the pure type, and it was destroyed. And those photos were taken by me. So you can see the bridge deck falling down, and the size move of the superstructure. So the girder was destroyed, and the shear failure of the bridge pier, and the flexural failure of the bridge pier that we can find. Okay, that we can find the damage situation at that time. So now, as you can see, this figure is illustrated for the reconstruction of the Wuxi Bridge. For this part, we just adapt a local reconstruction. However, for this part, because its damage situation is very serious, so we remove all the original bridge, and we use the new bridge pier between the original piers. And we consider use the steel plate girder because it is more lighter. So the self weight is less. So give the less influence to the burden of the foundation. And then also it can decrease the earthquake force. And in addition to that, we also use the best isolation. At that time, we consider the consideration of adopting of LRB, lead rubber bearing, or the high HDR, high damper rubber. They can be taken into account. And finally, the constructor used the high damper rubber to absorb the seismic energy. Okay, so this is the map of the reconstruction of the bridge. So this is the construction stage. It's the final photo. Okay, final photo. And after the CICHE earthquake, the Highway Bureau and Expressway Bureau are engaged on how to make the proper seismic retrofit and the evaluation of the existing bridges. So this slide shows some ways that we have used. The first one is retrofit of foundation. And the second one is steel jacking, a bridge pier and cap beam, and use of a damper device, and earthquake resistant concrete block and steel frame. And we use tie bar to prevent the deck falling down. And also we use the falling down prevention device. This is a case that we use the steel jacking of bridge pier. By this way, the flexural strength of the original pier cannot be increased significantly. However, its ductility can be increased. Okay. And this slide shows that we consider the earthquake resistant steel frame here. Okay. Because we have to understand that the space for reconstruction or for the seismic retrofit is not so large. So the seismic retrofit to have to consider the space need for construction. And this is Taiwan. We use at the end of Taiwan, we have to use the spring to absorb. As you can know, the Taiwan should be loose in the usual time because expansion joint, the functionality of the expansion joint will develop. If the Taiwan is tightened to prevent the expansion joint effect, it is not allowed. So when earthquake happened and a larger displacement was found, then the functionality of Taiwan will be triggered. Okay, and this is the damper device. We want to use the damper device to absorb seismic energy to prevent the damage, to decrease the damage of the bridge pier. And next one, I will talk about the strengthening of the scouring bridge. Okay, this slide shows at least the full bridge destroyed by the Typhoon Shilaka. Okay, as you can see, this is the Houfeng Daqiao, and this is for the Wuhuliao Xiqiao. This is Jiaxian Daqiao. This is Niumen Qiao. So you can see after the shock of the flood, the pier was destroyed. Then the traffic functionality of the bridge deck was interrupted. And those damage situation was caused by the Typhoon Morak. Okay, this is Qiwei Qiao, and this is the Shuangyuan Daqiao. As I mentioned, the change of the river bed from year to year. Okay, and this is the Tai Bridge. This is the Lai Bridge. You can see if the river is close to the mountain area, it means that it is close to the material provided by the debris flow. So lots of stone will gather at the beneath of the bridge. Okay, and if the location of the river is close to the sea, then the scarring situation is very serious. Okay, so this is the common way the Highway Bureau used when the bridge was destroyed. But we want to maintain the traffic smooth, so we use the RC pipe to let the water pass through, and then we can provide the temporary traffic functionality for the people. And this is the Shuangyuan Daqiao, and destroyed by the Typhoon Morak. And this is a very interesting example. And this is the Zhongzhen Bridge in Hsinchu County. Originally, there are 3 layers of protection of the river bed before the collapse of the bridge. For example, this is the time at 2005. We can see some damage was found at the third layer of protection device. And then to 2007, the destroy was totally happened to the third layer of the protection device. And then to 2008, the second protection device was destroyed as well. And then eventually, total protection device failure. Eventually, the bridge will collapse. So you can see the erosion situation is very, very important for the bridge engineer to consider in the design stage. Okay, so as you can see, this is the real case when the bridge was completed and open to the traffic. And few years later, the scarring depth becomes serious. And then how to make the strengthening is very important. And I just take an example of the Xizhou Bridge. Okay, as you can see, this is a Xizhou Bridge because the scarring depth is very serious. So now we use the foundation replacement work to do it. So the first step, we just implement the steel frame, the steel frame. The purpose of the implementation of the steel frame is that we want to change the load pass from deck to, originally from deck to the foundation, change to from the deck to the steel frame. By this way, we can remove the original bridge pier, because now the gravity load was transferred to the new steel frame. So the removing of the bridge pier is no problem. So you can see this is a construction stage. And after a completion of the bridge pier, then we remove the steel frame. It means that the loading path just go back to from bridge deck through the bridge pier to the foundation. Of course, we have to reconstruct the new pile foundation in advance. So this is the real case that we use. Okay, this is the case. So this is the original situation. The scouring depth is very serious. And then we use the foundation replacement work to implement a new steel frame to make the low pass changing. And then when the bridge pier was completed, then we dismantled the steel frame. So this is I use 3 photos to briefly introduce the construction stage of this bridge. Okay, so now we have faced lots of problems from the earthquake, from the flood, from the wind. So it means that we have to consider multiple hazards of infrastructure in Taiwan. So in the past few decades, we pay our attention on the research on these topics. And as you can see, this is a real video. I was in charge of bridge division at ANCRE. ANCRE means that the National Center of Earthquake Research in Taiwan. So at that time, I heard that our government will wish to dismantle the original 2 bridge deck. So I just asked them to offer the research center or research institute to do some test before it's dismantled. So then ANCRE spent about I remember maybe 7. I cannot even remember the exact total money. Okay, but we spent 2 months. You can see we implement a steel frame to support the original wall type as the retaining wall, and implement the actuator to put a cyclic loading on the bridge top. And we use the LVDT, and we use the displacement sensor to measure its displacement. So eventually we can have the hysteretic curve for being a civil engineering professor. You can see just a simple figure. It spends us lots of money, lots of labor to have this figure. So it is not easy to make a publication, compared to with the chemical engineering. Wow, they can have over 50 publication every year. However, for civil engineering, it is impossible. Okay, so we just did the test considering different scoring depths. So yeah, the more scoring depths, the less structural performance will be. Okay. And this is the test about the shaking table with considering the scoring and liquefaction. You can with the sandbags, and this is the simulation of the mass center of the substructure. This is a bridge pier, and we just consider the shake table, and we implement lots of sensor we want to make some comparison with the analytical result and the test results. And this is the excessive pore pressure the result we analysis and the experimental one. And you can see the results we got is very close to the actual experimental result. So it gives our confidence that in the future, when we consider the scarring problem, how to deal with this problem. And we want to make our research result to a practical application to the bridge engineering. And this is some result we have. And also the other problem is for the durability problem. As you can see, Taiwan is located in a subtropical climate zone. So the humidity, the temperature is high. So it is very easy for the material deterioration. So we usually we consider the reinforced concrete bridge damage, long-term damage due to neutralization and chloride invasion. So we just divide the Taiwan land by the grid with 1 kilometer and 1 kilometer, and we collect all the weather parameters related to the deterioration situation. So we just collect lots of inspect data and analysis data from the Highway Bureau. And we make the regression sieve equation to illustrate 4 different stages, including incubation period, propagation period, acceleration period, and deterioration period. Different deterioration period has a different corrosive speed. So according to the equation we regress, we can make a deterioration of the material all over the Taiwan map. Okay, so just according to the GIS, GPS, okay, we can have a we can understand the environmental influence to the material. And also we can make an estimation of when the cross-sectional area of the reinforcement 5% loss or 10% loss or 12% loss, the time need. So this is due to the chloride invasion. Of course, you can see those two figures are different because the chloride invasion zone is very close to the coast. Yeah, so this is our result. And also we combine the durability analysis to structural performance. So we can calibrate the structural performance from year to year. And this figure is very important for the bridge design. In case that the performance is below the threshold we set, then it means that something we have to do. So to consideration the durability, to maintain the durability of bridge structure, for the design stage, we have to consider the deterioration of structural performance. Okay, so this figure is very important. And also we combine the durability problem with the seismic problem. So as you can see, at the beginning of the completion of the bridge, T identical to 0, then its seismic capacity is this curve. And after 60 years of use, it decreased to the green line. So we can make the study about the relationship between the seismic capacity and the durability. And then how can we reflect the concept we gather to the bridge design in the future? Okay, this is a real bridge I designed. It's over 25 years. Yeah, it's a Mount Loshi Zhejiang Bridge. This is a Highway Bureau, and all the steel bridge were. I was the project manager of this case. Okay, so this is a cable stay bridge. Okay, also this cable stage, the span is not longer as the Galvin Street Bridge. However, the shorter span is 50 meters, the longer span is 100 meters. The ratio between the long span and the short span is 1.4, which is larger than the Gaobingxi bridge. And as you can see, the bridge deck was located on the curve. So at both ends of the section, the cable length is totally different. So the determination of pre-stress of the cable force is very important. Otherwise, the incorrect pre-stress applied to the cable force may lead to the bridge deck twist. Okay, so we have to consider the seismic analysis. So as you can see now, we use the time history analysis and to check the performance. Okay, we check the stress of the pylon and the cable force to check if they exceed the standard value. Okay, and this is the Gaobingxi CICHE, yeah, cable stay bridge. And of course, I have to emphasize that at that time, the computer efficiency is not so good. So now the structural analysis I did currently is not the one we consider 30 years ago. Okay, so as you can see now, the shorter span with 180 meter, we use reinforced concrete as a counterweight to make a balance with the longer span of steel deck. And now we have to consider the wind effect for the Gaobingxi cable stay bridge. We have conducted 2 times wind tunnel test. As you know that the wind tunnel test requires lots of money, require lots of time. We submitted the case to DMI in Danish. We have to line up. So because at that time, the aerodynamic analysis is not so popular, so we cannot do it. So all the problem related to the aerodynamic stability just can be done, just can be made sure by wind tunnel test. However, now, current technology, we can use the CFD, computational fluid dynamics, to do it. So now we use the numerical wind tunnel. As you can see, this is the deck of the Gaobingxi bridge. And we make the lots of density of a mesh close to the deck. And the other part, the density was loose. Okay, this is our mesh. And I have to emphasize that because according to the report of internal test made by DMI, the critical wind speed for the flutter of the Gaobingxi bridge is about 94.5 meter per second, I remember. So I just make a test. If now the numerical wind tunnel test we met, we consider the wind speed just a little bit less than the critical wind speed obtained from the actual wind tunnel test result. You can see the stability remains good. However, if we increase the wind speed exceeding the critical wind speed, you can see the stability cannot maintain. So you can see the effectiveness of the CFD seems it can be available to the practical bridge design in the future. And the next one, we'll introduce the composite bridge for emergency disaster relief. As you can see, because some bridges are in the mountain area, when the bridge was destroyed, somewhere may become an isolated area. The people, the food, the medicine can be transferred to the transport to the isolated bridge. So we consider because the large scale machine or large scale facility cannot move to the mountain area as soon as possible. So we developed a simple model by the cable stay bridge model. We want to just only few laborers can do the construction of the temporary bridge to make the transportation of people and the food and the medicine to the isolated area as soon as possible. So we have make the test. Okay, the photos shows that only I remember only 15 graduate students. They were working at the construction of the bridge close at the location close to the anchor. Okay, so you need 5 hours on and 43 minutes. Okay, and also we did the dynamic loading test. Okay, and to do the analysis, it seems that the result is reliable. 哎，不能动。下一页。Okay. Okay, this slide shows the ABC. Okay, I think the ABC is very famous and is very popular in the United States. However, in the United States, the precast bridge pier is available only for low risk area. However, as we can see that in Taiwan, there is no place belong to the low risk of earthquake. So we have a further study about how to make the application of BC in Taiwan. 不能动。Okay, we just use the concept of just like a legal type by stack block. 下一页。Okay, this is a detail. I want to skip it. Okay, so this is our test, and we just make the experiment in the inquiry lab, and we constructed one step by step, and then we just did the cycle loading test, and eventually we can see the right-hand side is the conventional cast-in plus reinforced concrete bridge pier. And this is the new type we propose. As you can see, for the conventional RC columns, the maximum bending moment will occur in at the bottom of the bridge pier. So it means that this pier, this part will absorb majority of seismic energy. So when the damage was happened, then the damage situation is very serious. However, we use the stack block. And you can see between the interface between each block, when the earthquake excited, the interface can open and close, open and close. It means that the seismic energy absorption is not limited only on the bottom of the bridge pier, but distributed to every interface. So when the seismic damage was occurred, the damage situation is insignificant. So we can see that the seismic capacity of the new type we propose at least is 1.2 times of that of the conventional RC columns. We also did the simulation to do it for the engineering application. This is a small test. As you can see, when the checking table tested and the interface between the stack block can open and close, open and close. It means that it can absorb the seismic energy distributedly. So the benefits of the two cases we propose, it means that we can, it just the small segment, a rapid construction and stackable and a factory precast. Okay, so the two cases we propose can achieve the short-term use, emergency clearance, personal and material transportation. And this one for short-term use, long-term use, and also it is available to use of the bridge pier and the house structure and retaining wall. Okay. And finally, I will give the bridge health monitoring and real-time safety. This is a video of the Nanpang Daqiao in Yilan County. As you can see, the bridge collapse suddenly. Okay, so it highlights the importance of the maintenance of the bridge. Okay, in addition to that, how to make a bridge monitoring is very important. So now I will show you a video about the monitoring system we developed. This is a real case we have achieved. Okay, now in this platform, at least we have 5 bridge monitoring cases. Okay, for example, we can make a choice of the bridge on the map and to take a look at its detail. This is arch bridge, and the symbolic means the location of the sensor. So you can see the signal of the sensor submitted to the head office from time to time, nearly real time, nearly real time. This is the displacement of the deck. The signal was transmitted every 3 minutes. Okay. And for the cable, we can establish the frequency spectrum. So if in case that the variation of the cable frequency becomes significant, then we can see what happened. Okay. And also we can take a look at the data of the specific cable or the specific displacement of the deck during some periods. And we can watch the variation. Okay, and also we can make the report automatically, no man-made, no man-made. Just make the report automatically by our platform. So you can see if the signal exceeds the threshold value we set, our platform will pass the signal to the bridge manager. Okay, next one. Okay. And also we have a big data bank of all the signals. Just like the human beings, if we can keep the resume of a health situation, it benefits our health management. For example, if our pressure, blood pressure or heart rate, if we can have the data, then maybe someday the data just seem unusual. So it seems that we have to take care of ourselves. And the signal exceeds the threshold value significantly. Okay, that it seems that there should do something. Okay, so that's the video I played. 可以下一页吗? Okay. So here comes my some conclusions. Okay, I think in the future, if we want to make a decision corresponding to the global climate change, I think the climate informed design and planning is necessary, and adaptive design and natural infrastructure. It means that we can consider the natural material to be used, and we have to develop advanced engineering technologies. And the most important is that the risk assessment early warning system is needed, and infrastructure maintenance and upkeep. And then the community engagement and education. I think now going to the AI age, the education is very important. Just like President Hughes mentioned, all the making decision should be determined finally by the expertise engineers. Otherwise, the making may be incorrect. So the education is very, very important, okay? And also we have to provide a resilient transportation to shorten the recovery time we need after the damage has happened. And also we have to develop green and sustainable infrastructure. Actually, in my lab now, we are currently engaged on the design specification of offshore wind turbine structure in Taiwan. Okay, so we provide the guideline for the design of the offshore wind turbine technology. And I just make an announcement. On October 27th, we will make a conference to announce the software we developed. It can significantly shorten the computer time. Okay, of course, we need a policy and regulation provided by our government. And for the client, we need the investment and the funding. That's all my presentation. Thank you very much.
Thank you, Professor Soms, for the wonderful sharing. And any questions for Professor Som? Any comments? Okay, so we'll move on. No? Oh, okay. There's one.
Thank you for the presentation. On page 44, you experimented the bridge transversely, transverse direction. And my question is, have you tried longitudinal direction? It seems that transversal direction only. So my question is, have you tried longitudinal direction?
Loading test.
Hi.
Yes, we conducted a loading test inside, as the video shows, and
But
we measure the force and the displacement longitudinal.
I think this
no,
direction is the transversal.
I see. No, in this case, we just applied our test in the transverse direction. Assume that it's not easy to do the site test, okay? Because the government give us demand that we have to complete the test not over than 3 months. So we did the test 2 months. So we have enough time to do the test along the longitudinal direction. Okay.
Because we simulate the earthquake in the computer modeling. Well, generally we try longitudinal and transversal. So that's why I ask you. Okay, thank you.
Okay. Yeah, I think, of course, the seismic consideration of the bridge deck usually governed by either longitudinal direction or the transverse direction. However, through the test, we can confirm that our analysis result gives a good agreement with the test result. So we have the confidence that also in the longitudinal direction, we can use the analytical method to understand its actual seismic behavior. That's our purpose. Okay, thank you.
Any more questions or comments?
Your designer, are you calculation of the liquefaction in your design?
Yeah. Actually, in our seismic design code, some important issues for consideration of liquefaction is addressed. So for the engineers, we have to obey the regulation specified in the seismic design code. And our deeper study is one to understand the more detailed information for the soil under liquefaction. For example, as the slide I showed, we want to realize the excess pore ratio between the soil. You know, for the detailed item, it is not very difficult to specify in the design code. However, we want through our research, we can have more information about the detailed items. Okay, that's our purpose.
Thank you. Thank you.
Thank you. Excuse me, I don't know what you mean. Yes. You mean paper? Power station. Mm -hmm. You mean the clearance? Sorry, I don't know what you mean. Uh-huh. Mm-hmm.他说什么 ？Power station 没有 power station。Power 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 station。I think in my presentation I didn't talk about something related to power station. Scoring. Scoring what? Oh, 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 I see, I see, I see, I see. OK， 那个大甲溪的那个。OK， sorry, I misunderstood. Yeah. Yeah, originally the clearance between the bridge deck and the sea river bed is over 10 meters at least. And eventually the storm occupied the bridge deck. So terrible of the typhoon. And one, yeah, Guguan, but now its functionality is good. Yeah, no longer the use. Yeah, no longer. Sorry.
So thank you, Professor Song, for the wonderful sharing. And here's the announcement.
Hello. Okay, thank you. And then thanks for everybody coming here. And I have to make several announcements. We will prepare lunchbox for you. There's only two choices. Okay, near the registration desk. One is a vegetarian, the other is a chicken. And then just take your lunchbox and then on the table there. But I would like to remind, you can have the lunch here, but after lunch, please assist us. You have to you have to know when you turn please you have to itemize either the trash and the box. You finish your lunch, and also maybe the leftover. You have to know there's 3 boxes there. Please just return that, and for each box based on the item you finished your lunch. That's my announcement. This afternoon, and then we have a 3-power session. This session here was CICHE and JICE joint workshop, and then we are talking about green energy technologies in this room. And there's another 4 session